Okay, so today we're continuing our journey through chapter 7, looking at the different conic sections. So remember, the reason why these curves are called conic sections is because they result from slicing a cone and looking at the curve of intersection. And so we've already talked about circles and parabolas. So I already talked about those two. Today we're going to talk about the ellipse. And so the way you get an ellipse is you slice the cone at an angle, but not too far. Not straight across to get a circle, but at an angle here to get an ellipse. That's the geometric way to get an ellipse. You can get an ellipse. Let me show you that visual here. So I think this is a pretty nice visual, once again, from Dr. Talman, where we can see the ellipse there being cut. So there's the circle, and then there's the ellipse. I like to think of the ellipse as sort of a cousin of the circle. Okay, so a week ago we talked about circles, and to get a circle you fix a point called the center, and you look at all points that are a fixed distance from that center, namely distance r. That's the radius of your circle. For an ellipse, you fix 2 points. Each of these points is called a focus. And when you have more than 2 focus, the plural of focus is foci, or also foci, depending on how you want to pronounce it. And to be on the ellipse, the sum of the distances is a constant. So here r was a constant distance from a point on the circle to the center. Here, the d1 plus the d2 is always a constant. So instead of comparing your distance to just one point like you do in a circle, you're looking at the sum of your distances to 2 points. Now we have a visual for that again, courtesy of Dr. Talman. If you wanted to construct an ellipse at home, you could take maybe a piece of cork board, put a piece of paper on it, and put 2 thumbtacks, and put a piece of string between the 2 thumbtacks, and hold a pen taut and trace around to get your ellipse. Here we've got a visualization of that. So you can see that on the bottom there, you see that the red line segment plus the blue line segment, that length stays the same as we walk around the ellipse. So you can imagine putting your thumbtack at each focus and then keeping the string tight as you move around. That would trace out an ellipse. Okay? Algebraically, you can think of an ellipse as a circle where we've stretched more one way than another. And so algebraically, we had our equation for a circle. Oops. We had x minus h squared plus y minus k squared is equal to r squared. And then we looked at it as x minus h squared over r squared plus y minus k squared over r squared equals 1. When we talked about deforming the unit circle into any circle. And so we can think of this as the center is hk, and we move r units in the x direction and r units in the y direction to get to the points on the circle. So we connect those up. So with an ellipse, the algebra is nearly the same, except we're going to go more in one direction than another. So we can have some number a squared here and some number b squared here. And so for an ellipse, we're going to start at the center point like we did before, but we'll go a units in the x direction and b units in the y direction. And that's going to stretch us more in one direction than another, and that gives us an ellipse. All right. So once again, just like these, all the other conic sections, the circles and the parabolas we've looked at, there's a geometric way to think about them by slicing a cone. Algebraically, they're the graph of a quadratic equation. In this particular case, for an ellipse, both variables are squared, but the coefficients are going to be different. And ultimately, that algebraic representation comes from a distance formula. Now, with circles and parabolas, we went through the derivation. The derivation for the ellipse is in the book. We go through it in painstaking detail. But with the ellipse, not only comes the graph in the center, but also we have to look at locating the foci and everything else. So we're going to spend our time today focusing, pun intended, on graphing the ellipse and then being able to find all of its various parts. Just like the focus of a parabola, the foci of the ellipse have to do with a reflective property. And so if you imagine having something emanating from one focus, sound waves or light waves, when they bounce off the ellipse, they will get concentrated at the other focus. So in the text we have an example of the whispering galleries. So in a whispering gallery, if you stand at one focus and you whisper, the person that the sound waves you make as you whisper are going to bounce off the ellipse and get reflected right back to the person at the other focus. So it can be a very unnerving thing. And there are several examples of this in architecture. You can just stand and whisper, and then a person all the way across the room, it'll sound like they're talking right in your ear. So it's pretty creepy. Apparently John Quincy Adams exploited the whispering gallery in the Senate Rotunda to spy on his enemies. So I'm not sure how true that is, but anyhow. Another important application of the ellipse involving its foci is that Kepler proved, well, that's not showing up very well. Kepler proved that the planets actually orbit the sun in elliptical orbits, and the sun is at the focus of that elliptical path. So here's some formulas relating to the anatomy of a focus, or the anatomy of an ellipse, and we'll introduce these as we go through today. So first we're going to focus, like I said, pun intended, on graphing them, and then we'll come back and fill in the bits and pieces. All right, so the handout on ellipses starts with a review here. This alternate standard equation of a circle, and then we can see how it's related to the ellipse. So it really is a cousin of the ellipse, where instead of stretching both the same amount in both the x and y directions, we stretch different amounts. And so our first example here, we're just going to be graphing these things, and then we'll come back and fill in all the bits and pieces. So we want to graph 25x plus 1 squared plus 9y minus 2 squared is equal to 225. It's 25x plus 1 and 9y minus 2. All right. Now, we've had circles, parabolas, and now ellipses. And so we need to be able to take a look at the equation they give us to try to figure out which of those conic sections it is. So one thing to note here is that both of these variables are squared. X and y are both squared. That means it can't be a parabola. Because to be a parabola, we're only going to have one variable squared. So now we look at the circle. Circle have both variables squared. It's a sum of squares. But in the circle, the coefficients would be the same, and here they're different. So the fact that we have both x and y are squared with different coefficients, all right, and they're being added, that tells us we've got ourselves an ellipse. All right. So the standard form of the ellipse is x minus h squared over a squared plus y minus k squared over b squared equals 1. So that's the standard form we're shooting for. So we need perfect square quantities. We need the sum to be equal to 1, and we need to write what's happening here as fractions. So the formula they give us, the equation they give us, is nearly in that form. I've got perfect squares. I just have to get the thing equal to 1 and then rewrite as fractions if needed. So I'll divide both sides by 225. And I'll get x plus 1 squared divided by 9 plus y minus 2 squared divided by 25 equals 1. And so right away what this tells us is that the center, we get the center the same way we got the center with circles. We take the opposite here. You see an x plus 1. That really means the center is going to be at x equals negative 1. You see a y minus 2. That means it's the center is going to be at y equals 2. The a squared here is 9. So the a is 3, which is how far we're going to move in the x direction. The b squared here is 25, which means the b is 5, and that's how far we move in the y direction. So we're just going to start at negative 1, 2, move left and right 3 units, and move up and down 5 units. So here's my x and y. Center negative 1, 2. So I'll put a little cross there. I'm going to move 3 to the left and right, 5 up and down. So 3 left and right, 1, 2, 3, 1, 2, 3, and 5 up and down. 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Now to kind of assist in the drawing here, we can dot in what I like to call a guide rectangle. So it just kind of helps us, in theory anyway, graph the thing. And we're going to have these extreme points here. And then we're going to sketch the ellipse there inside the guide rectangle. Let me move this over a little bit so it lines up, and here we go. All right, that's an ellipse. Okay, so that's how you graph it. You put it into the standard form. You find the center the same way you found the center with circles. And then you look at the denominator. You take the square root of the denominator. The square root of the number under the x tells you how far you go in the x direction. The square root of the number under the y tells you how far you go in the y direction. All right. So once again, in the language of transformations, the center is coming from the horizontal and vertical shifts, and the scaling is how far left and right, up and down you go. Those are the horizontal and vertical scalings. Okay, so with the circle, all we had was the center and the radius, and that completely determined the circle. For the parabola, we had the vertex, the focus, and the directrix. So with the ellipse, there's a lot of stuff we need to find that goes along with the ellipse. There is the center, which we found, negative 1, 2. But there's also the foci, so where the focus points are. So once again, the parabola had one focus, the ellipse has two. We also have vertices. We have more than one vertex with an ellipse. We call those vertices. And we have the major axis, and we have the minor axis. All right, so let's talk about what each of these things are in terms of this particular ellipse. Well, let's do the major axis and the minor axis first. In this particular ellipse, we have two lines that go through the center here. We've got the line up and down, the vertical line, and we've got the horizontal line. The line segment along which the ellipse has been stretched the most, that's called the major axis. So in this particular scenario here, we have the center at negative 1, 2. We've got this line segment, the green line segment, lies along the vertical line x equals negative 1, whereas the red line segment lies along the line y equals 2. The ellipse has been stretched further along the vertical line than it has the horizontal line. So we would say that the major axis lies along the line x equals negative 1, and the minor axis lies along y equals 2. So when they ask for the lines which contain the major axis and minor axis, one of them is always going to be the x-coordinate, x equals. In this case, x equals negative 1. The other one's going to be the y equals 2. Any questions on how to figure out which is the major and which is the minor? Major, think bigger. Okay? Now, the vertices, these are where the ellipse crosses the major, well, I should say this way. These are the endpoints of the major axis. I'll just write it that way. So once you identify the major axis, the vertices are going to be these 2 points here. So these are the vertices. So in this particular case, what are the vertices? Well, I started at negative 1, 2, and I moved up 5 units and then down 5 units. So if I move up 5 units, I'd be at negative 1, 2 plus 5, which would be negative 1, 7. And if you move down 5 units, it'd be at negative 1, 2 minus 5, which is negative 1, negative 3. So the vertices are always 2 of the points you initially plot for the ellipse. It's the endpoint of the major axis. Now the foci lie along the major axis as well. And the question is, how far do we go to get to the foci? And so once again, the formula here that we're going to use comes from the derivation of the ellipse using the distance formula. Okay. So if you've got an ellipse, we're going to let C denote the distance from the center to each focus. All right. It turns out that C equals the square root of, well, we could write it compactly as the absolute value of a squared minus b squared. Another way to think about it is this is going to be the bigger of a squared or b squared minus the smaller of a squared or b squared. So in this particular scenario, the a squared is 9, the b squared is 25, so C would be the square root of 25 minus 9, which is the square root of 16, which is 4. So the foci are 4 units from the center, and they lie on the major axis. So C is the distance from the center to each focus. It's the square root of, in this case, 25 minus 9. And so we have the foci are 4 units from the center on the major axis. So if I go back to my diagram here, and I want to figure out where the foci are, I'm going to start at the center and move along the major axis. So once again, just like with the vertices, I'm going to move up and down here. If I start at negative 1, 2, and I move up 4 units, I'll be at negative 1, 6. If I start at negative 1, 2, and move down 4 units, I'm at negative 1, negative 2. And so those are the foci. Now, the last thing we can talk about when it comes to ellipses is the eccentricity of an ellipse. And this is called E. Now, it's context specific. We just got done with exponential functions and all things base E in chapter 6. Now we're using the lowercase e for a different reason. Eccentricity. So when you think about something being eccentric, you think of it being a little off. The eccentricity is a measure of roundness. The eccentricity is defined to be the distance from the center to the focus divided by the distance from the center to a vertex. So the distance from the center to the focus, that's what we call C. The distance from the center to the vertex, that's either A or B, whichever is larger. All right. Now, because of how ellipses are built, the foci are always closer to the center than the vertices are. And so the eccentricity is always going to live between two values, 0 and 1, because the foci are always closer to the center than the vertices. The closer you are to 0, the rounder you are. More like a circle. All right. So in our particular case, the eccentricity of our ellipse E, well, the distance from the center to each focus, that's our value C, that's 4. And then from the center to the vertex, that's a 5. So our eccentricity would be 4/5. Okay. So that's graphing the ellipse, and that's finding all the assorted pieces. Once again, in the applications, it's going to be important to know how to find the focus of an ellipse, or given the foci of the ellipse, build the ellipse, things like that. Okay. Any questions on finding any of those bits for this particular example? All right. So let's go off to Desmos here. And let's check our well, let's look at a generic ellipse here. Oops. X minus h squared over a squared plus y minus k squared over b squared equal to 1. Oops. Add sliders for all those things. And let's get this thing centered at the origin, so we'll do 0 and 0 on that. There we go. And then what we'll do is we'll actually plop down the foci here. Let's make A bigger than B. So we'll stretch A out this way. And we'll look at where the foci would be. So they would be the square root of A squared minus B. Well, I'll just put absolute value here. A squared minus B squared comma 0. And we'll label that as, call that F1. And then we'll have the same thing. And put the negative there. We'll call this F2. And we'll be consistent here with the colors. So there we go. So this concept of eccentricity here, I'll call E equals C over A. And will it calculate that for me? No, it will not. Well, we'll just go through it manually here then. So we can see here, my B is 1. Let me make my B. Whoops. Let me make my B a little bit bigger here, and look at the A. So we can see here, like if A is 4 and B is 5, there's eccentricity for and you can see what happens to the foci as the A gets closer to 5. So when the A is far away from 5, as the A gets closer to 5, you can see the foci are moving closer together, and it's getting more and more round. Okay. The further I get away from that, it's getting less round. Okay. So this would be an eccentricity getting close to 1, whereas this is an eccentricity getting close to 0, because, as that C, the distance from the center to each focus, gets close to 0, the foci are collapsing down. So you can think of the foci are coming together, and that would collapse down to a circle, and the two foci would collapse down to the center. Okay, so that's the concept of eccentricity, sort of visually for you. All right, let's move on and do the same thing for this next equation. So this next equation, we have to do some work to get it into standard form. We'll get it into standard form, graph it, and then we'll find all the bits and pieces to it. So we've got x squared plus 4y squared. So it's x squared plus 4y squared minus 2x plus 24y plus 33 equals 0. So let's double check. There we go. Okay. So we've got a lot of work to do. But once again, the first thing we want to do is figure out what conic section we're dealing with here. So I notice I've got x and y. They're both squared. They're both added together. So that means that it rules out a parabola, because in a parabola only one variable is squared. Since the x squared and the y squared have different coefficients, I know that's not going to be a circle. So I know I have an ellipse on my hand. And so my goal for the ellipse is to get it into the form x minus h quantity squared over a squared plus y minus k quantity squared over b squared equals 1. All right, so that's my goal here. So I need completed squares for x and y. I need everything equal to 1, and I need to rewrite things as fractions if they're not as fractions. So the first step towards that is we're going to subtract the negative 33 over, and we'll group the x's together, and we'll group the y's together. So I'm going to have an x squared minus 2x plus 4y squared plus 24y equals negative 33. And now I need to complete the square on the x and the y. So the nice thing about the x's is that the leading coefficient of x squared here is already 1. So I can go ahead and leave space for what the completed square is going to be there. For the y squared, I've got a 4 in front of the y squared, so I got to factor that out. And once again, I'm going to leave space. So here's the recipe once again that we talked about last week. What I need to do is I need to take this number, the coefficient of x, I need to cut it in half, and then I need to square the result. So cutting this in half would give me to a negative 1. When I square negative 1 squared, I get a positive 1. Plus 4 times y, once again, coefficient of y. You're going to cut that in half to get a plus 3. And then I'm going to square it to get a 9. Equals. And I had to add some stuff to the left-hand side of the equation, so to keep the balance, I got to add the stuff to the right-hand side of the equation. Now, as far as with the x, I had to add a 1 here. So I got to add a 1 to the other side. I added a 9 for the y quantity, but that's inside a quantity multiplied by 4. So what did I really add? A 36. So when the dust settles here, I get a 4. And so now I've got my perfect square quantities. So now I have to get everything equal to 1. So I'm going to divide both sides by the 4. And then we'll flip over to the next screen. Any questions on completing the square? So on the next page, we're going to have an x minus 1 quantity squared divided by 4 plus a y plus 3 squared, and the 4's would cancel out there, equal to 1. But if I want to write this as a fraction, I could write this as x minus 1 squared over 4 plus a y plus 3 squared over 1. And now I can tell quickly that the center here is 1 comma negative 3. The a squared is 4. So that means that a is going to be the square root of 4, which is 2. So that's how far I'm going to move in the x direction, left and right. The b squared here is 1. So the b is the square root of 1, which is 1. And that's how far I'm going to move in the y direction. So let's hop over now and graph it, and then we'll find all the bits and pieces. Now, we don't have to use one block equal 1 unit. All right. In order to try to keep things from getting too crowded, in this case, we can do like 2 blocks as 1 unit. So let's do that. Our center here is at 1 comma negative 3. So 1 would be, there's a half 1, a half negative 1, negative 2, negative 3. So here's our center. And from the center left and right, we're going to move 2 units. So a half 1, a half 2, a half 1, a half 2. And in the y direction, we're moving 1 unit up and down, a half 1, and then half 1 and 1. And we can, once again, sketch in our little guide rectangle. We've got our 4 points here. These are the endpoints of the major and the minor axis. And now I connect the dots. There it is. All right. Now we have to find all the bits and pieces of it. So the center, once again, was at 1, negative 3. Oops, I got my slides out of line there. So 1, negative 3. So let's figure out which is the major axis, which is the minor axis. So once again, the major axis is the line segment, and the minor axis is the line segment that goes through the center. The major axis is the longer of the two. Okay, so our major axis here lies along, well, which line here? So we've got x equals 1 and y equals negative 3. It's the horizontal line here, y equals negative 3. The minor axis lies along the vertical line here, which is x equals 1. Any questions on identifying the major axis or the minor axis? Where they live there. So remember, the vertices and the foci all live on the major axis. So for vertices, I look at the endpoints here of the major axis. So these are my vertices. So I started at 1, -3, and I moved left and right 2 units. So I'd be at 1 plus 2 comma -3. So 3, -3 would be this vertex. And then 1 minus 2, -3 would be -1, -3. That'd be the other one. So the vertices are the endpoints of the major axis. So from the center, you move left and right, either horizontally or vertically, to get to 2 of the points that you plotted initially to graph the ellipse. Now we need to find the foci. And so for the foci, we need to figure out that value c. Remember, c is the difference of squares, the bigger square minus the smaller square. So in this case, c is going to be the square root of the 4 minus the 1. So that's root 3. The foci also live on the major axis. So I'm going to start at the center here, 1, -3, move root 3 units to the right, and then root 3 units to the left. And that's as good as we can get it. The square root of 3 doesn't simplify to a nice, friendly, rational number, so we'll just leave it as 1 plus root 3, -3, and 1 minus root 3, comma, -3. Now, if I wanted to try to sketch that on the graph, root 3 is about 1.6 or so, so this is roughly 2.5. So if I start here, it's going to be near. It's tough to see where they're going to be, but they'll be like over here and over here. And for my eccentricity, well, the distance from the center to each focus was root 3. The distance from the center to each vertex was 2. That would be root 3 over 2, which is, pretty close to 1. As you can see here, the ellipse is not very round. Any questions on putting the ellipse in the standard form? It's our old friend completing the square. This is the 3rd time we've seen completing the square. Hopefully it's getting easier the more times you work it. You need to first identify what conic section it is to know what formula to get it to. Complete the square. Identify the center, a squared and b squared. And then everything else kind of works from the graph. Okay. All right. All right, number 2, graph this function. And once again, it's like, what's this doing here in the section on ellipses? Well, this is actually part of an ellipse. It's actually an ellipse in disguise. And so let's talk about this. Remember, when you graph a function, f of x, you're graphing the equation y equals f of x. So we're graphing the equation y equals 1 plus 2 square root minus x squared minus 4x minus 3. And so the claim is this is actually part of an ellipse. So to see that, let's subtract that 1 over. And let's divide by 2. And now we'll square both sides. Excuse me. So we have a y minus 1 squared over 2 squared, which is 4, is equal to negative x squared minus 4x minus 3. Let's get the x squared and the x over to the other side. We'll add them on over. Leave a blank for completing the square. Complete the square, x plus 2 quantity squared plus y minus 1 squared over 4 equals. Right? Cut this in 2 and then square it. Add that to both sides. Boom. So check it out. We have, in fact, an ellipse. The center of the ellipse is at negative 2, 1. The a squared is 1. So the a is the square root of 1, which is 1. The b squared is the 4. The b is the square root of 4, which is 2. Now all we're asked to do is graph the function. So all you're asked to do is graph. You don't need to find the foci. You don't need to find any of the other stuff. You just need to graph the thing. Okay? Only give the information I ask you to. I don't want you to be doing more work than you need to. So let's look at here, center negative 2, 1. So negative 2, 1 is the center here. And we're moving 1 in the x direction and 2 in the y direction. So 1 in the x. Well, I guess this might be a good one also to have each block here be half a unit. So we want negative 2, 1. So negative a half, negative 1, negative 1 and a half, negative 2, a half 1. So there be our center. Moving 1 in the x and 2 in the y. So 1 in the x, 2 in the y. There's our guide rectangle. And here would be our ellipse. All right, whoops. So here's the thing. The graph of this ellipse is not the graph of a function because it fails a vertical line test. So we only want part of this ellipse. And the question is, which part do we want? Well, if we look at going back to the original equation we were going to graph, notice that the y is equal to 1 plus stuff. That means that the y coordinates on this graph are always bigger than 1. So I only want the upper half. So here's the y equals 1 line. I only want the upper half. And so the red here is the graph of y equals f of x. So just like when we had circles and we had to pick the upper semicircle, lower semicircle, same thing with ellipses. We're going to have to pick half of it depending on what we want. If we were trying to figure out the graph of y equals 1 minus this, minus means we want things below. So the bottom half here would be y equals minus 1 minus the 2. I guess I can just draw an arrow to that. Okay? Any questions on that example? All right. Then as usual with these conic sections, we've got a couple where we turn the tables. So instead of me giving you an equation and you graphing it and finding parts, here's where the parts are. Turn around and graph it. Find the standard form of the equation of an ellipse which satisfies the following characteristics. So just like when we built parabolas and built circles, what I like to do is I like to start graphing it out. So this is taking some algebraic information and looking at it geometrically to help us out. So the foci are at 2, 1, and 4, 1. So 2, 1 is where one focus is, and then 4, 1. And there's a vertex at 0, 1. Now from that, we got to work backwards. So here's the equation of an ellipse. X minus h quantity squared over a squared plus y minus k squared over b squared equals 1. So we're going to work backwards. First thing we can find is the center. Remember, the center is the center of everything. The center is always going to be the midpoint between the foci. It's also the midpoint of the vertices if we had the other vertex. So what's that going to be? Well, I've got 2, 1, and 4, 1. So it's going to be the average x, 2 plus 4 over 2, and the average y, 1 plus 1 over 2. So it's going to be at 3, 1. And you might have been able to just spot that, right? I mean, that's what's halfway between. But in general, if the numbers are a little funkier, it's just a midpoint. So that's cool. So we've got that figured out now. So it's going to be x minus 3 squared over something plus y minus 1 squared over something else equals 1. So we got a 2 for 1 there. Now we got to figure out what's A and what's B. All right. So since the foci and the vertex are to the left and right of the center, I know that A is going to be the bigger of the two. So the major axis is horizontal. So that means that A is going to be bigger than B. So we want to keep that in mind. And remember what A is. A is how far you go from the center out in the x direction. So I can calculate this now. Because the center is at 3, 1 and the vertex is at 0, 1. So that's going to be 3 units. So the A here is 3, so A squared is 9. So a 9 is going to go under there. Any questions on how we sorted that out? So the last thing I got to figure out is the b squared. All right, I don't have any point on the graph that's above the major axis. So I don't have any idea how far up and down this goes from the information given, but I think back to where else I use that b when I graph the ellipse, and it's in the equation for finding the foci. So c, remember, is the square root of the bigger of a squared minus the a squared and b squared minus the smaller of a squared and b squared. Here a squared is bigger. So this is going to be a squared minus b squared. C is the distance from the center to each focus, which once again, now that I know what the center is, I can find this. That's just 1 unit. So 1 equals the square root of a squared, which is 9, minus b squared. So I can square both sides. I can add the b squared over and subtract the 1 to get b squared is 8. And there it is. Any questions on reverse engineering this ellipse? So when in doubt, graph it out. All right. When they give you information like this, you can go nuts trying to just plug stuff in the formulas. Draw a picture, right? That's one of the big themes in the class is taking information, representing it different ways, algebraically, geometrically, and then working backwards from the picture. Okay, next example, they just give us a picture. Here's the ellipse graph below. Got to find the equation of the ellipse. So let's see. So it looks like they've labeled the points 0, 0, and 6, 0. That's good. Let's see what we can get out of that. Once again, here's our formula we're trying to get to. Now the h and the k, that's the center. Remember, the center is the center of everything. So if I look down here, I'm given these 2 points, 0, 0, and 6, 0. And the center of that's going to be at 3, 0. So I can tell that the center is at 3, 0. Once again, you could go through the formal midpoint calculation if you need to get that. So there we go. That's our h and k. And so I'm down to this equation now. Now, they give us the point 1, 3. Notice they don't tell us what this point is. It looks like this may be, it may be 3, 4, but they didn't label it as 3, 4. So we're not going to assume anything unless we absolutely need to. But one thing we do get from here is that it's stretched further in the y direction than it is the x direction. So if we need to figure it out, the b squared should be bigger than the a squared when we're all said and done. Okay. All right, so how do we proceed from here then? We're not given information about the foci. We don't have the points there of the major axis. So in other words, the major axis would be vertical, right? The minor axis in that. But they do give us some points. So what we can do is plug the points in and see what we can get. So here's our equation so far. So we know the center's at 3, 0. And we know that in the x direction, we're getting the points 0, 0, and 6, 0. So this tells us we're moving what? 3 units in the x direction. That gives us that a is equal to 3. So a squared is 9. So now all I got to do is figure out what the b squared is. So once again, I'm going to go up here and use the point I've got 1 comma 3. So the fact that 1 comma 3 is on the ellipse means that when I plug in x equals 1 and y equals 3, I should get a true statement. So plugging in x equals 1, I get a 1 minus 3 over 2, 1 minus 3 squared over 9, plus 3 squared over b squared, that equals 1. So I've got a negative 2 squared is a positive 4, so 4/9 plus 9 over b squared is 1. If I subtract off the 4/9 from both sides, I've got 9 over b squared equals, and if I want, I get a common denominator here. 1 minus 4/9 would be 9/9 minus 4/9, which is 5/9. And then I could do, ratio proportion, cross multiply, however you want to say it. We would get 5b squared equals 81. So b squared would be 81 over 5. Any questions on finding the b squared there? So if I go to put that into my formula, x minus 3 squared over 9 plus y squared over b squared, that'd be y squared over 81/5 equals 1. We could write that as 5y squared over 81 equals 1. And just a little note here, if I look at, the b squared being 81/5, so b is the square root of 81/5, that's close to 4. Okay, that is close to 4. It's a little bit bigger than 4 though, but it's not exactly 4. So that's why it's important to use, you only guesstimate points on graphs unless you absolutely need to. In this particular case, we had enough things labeled to get us to the answer. Okay? All right, and once again in the homework, you'll have some exciting applications of the ellipse using the reflective property, looking at the foci, orbits of planets, whispering gallery, stuff like that. Let's take a look at your next take-home assignment. So this is what you can be working on. So remember, in addition to the weekly take-home assignment, there's that final assignment that you can be working on as well. So I try to keep the end of the semester. I don't try to overload you in the last month of the course because there's no need to, but I want to make sure you have enough time to start working on things as we finish up the course here. Let's take a look here at take-home 12. Can you believe it? Take-home 12. So take-home 12. Due next Wednesday. Your progress report on your project is also due next Wednesday. So you got this solar cooker. It's a paraboloid of revolution. So we mentioned this on Tuesday, that the focusing property of the parabola can be used for satellite dishes and flashlights. It can also be used for solar cookers. So what happens is you've got this shape, which is in cross section, it's a parabola. So if you look at the cross section, it's going to be a parabola. And what happens is the sun rays come in and they bounce off the mirror and they get concentrated at the focus, which means you can put something in there and actually heat it. All right, and you can actually buy these. They're called solar cookers, tailgate solar cookers, and they use these reflective properties to help you do it. And so here's an actual honest-to-goodness one. It says it has a diameter of 1 meter and is 0.5 meters deep. So that means that if you look all the way across the solar cooker, it's 1 meter. And if you look at how deep it is, it's 0.75 meters. We're asking for the focal length, the distance from the vertex to the focus. That's this value P. of the cooker. All right. So this is one of those situations where you're kind of free to make the vertex wherever you want it. So the easiest place to make the vertex would be at the origin. Whoops. So that your equation here would be x squared equals 4py. And now you use your information to figure out, if we're trying to look for p, you got to figure an x and a y coordinate. All right. So using this information, you should be able to get an x and a y value that you can plug in to find p. And that's all there is to it. Okay. Students tend to overcomplicate this problem. Maybe they get distracted because of the cool picture. I don't know. But this is an important thing, because you can imagine, if you're out in a place where there's not electricity, or the electricity goes out and you want to find a way to boil water or cook food, you can have the sun do it for you. And the most efficient way to do it is to have an apparatus like this that focuses the sun's rays. Okay, so that's how you get you going there, number one. Number two, a little less exciting problem, I admit. Put the following equations in standard form and graph. Okay, so notice it just says graph. All right, standard form and graph. So whatever you need to graph it. So unless you want to, you don't have to find all the parts and write them down. The first one there, notice only one variable is squared. That should give you a hint as to what conic section that is. Put the standard form, rewrite it in standard form, complete the square if necessary. Number two, we've got a sum of squares, different coefficients. That's like what we did today. Okay. And then the last one is to graph this equation by showing the graph as part of an ellipse. So this is like the last example, or the last graphing example we did just a few minutes ago. All right. Alrighty, folks. Well, as always, I appreciate you tuning in. Stick around if you have questions for office hours. Otherwise, I hope you get out and enjoy the sunshine here the next couple days. And if I don't hear from you, we'll see you back here on Tuesday.